In this session, we are going to explore a fascinating construction in the theory of functions, the integration of Riemann's function r of x. This specific trigonometric series is famous for its complex behavior and fractal-like properties. Our goal today is to go beyond the surface and precisely evaluate its definite integral over an arbitrary interval. First, let's look at the problem statement. We define the function r of x by the following trigonometric series. R of x equals the sum from n equals 1 to infinity of 1 over n squared times the sine of n squared pi x. Our objective is to evaluate the definite integral of this function, denoted as I, over an arbitrary finite interval from x1 to x2. Before we proceed, we must address the validity of term-by-term integration. We need to mathematically justify interchanging the summation and integration operators, as this operation is not always valid. To establish this, we examine the uniform convergence of the series using the Weierstrass M-test. Observe that for any real number x, the sine function is bounded by unity, so the absolute value of the sine of y is less than or equal to 1. Consequently, the absolute value of our general term satisfies the inequality 1 over n squared times the sine of n squared pi x is less than or equal to 1 over n squared. The numerical series, the sum from n equals 1 to infinity of 1 over n squared, is convergent. This is a classic result known as the Basel problem, where the sum equals pi squared over 6. It follows that the functional series converges uniformly on the entire real line. Since the individual terms of the series are continuous functions, and the convergence is uniform, the sum, r of x, is necessarily a continuous function. A continuous function on a finite interval is Riemann integrable. This uniform convergence provides the sufficient condition to integrate the series term by term. Now, let's move to the step-by-step derivation. We express the integral of the sum as I equals the integral from x1 to x2 of the sum from n equals 1 to infinity of 1 over n squared sine of n squared pi x dx. Based on our theoretical justification, we interchange the order of operations. This gives us I equals the sum from n equals 1 to infinity of 1 over n squared times the integral from x1 to x2 of the sine of n squared pi x dx. Now, we evaluate the integral for the general term n. Recall the standard antiderivative. The integral of sine of kx dx equals negative 1 over k times the cosine of kx. In our context, the constant coefficient k is n squared pi. Applying this, the integral of sine of n squared pi x dx equals negative cosine of n squared pi x divided by n squared pi, evaluated from x1 to x2. Applying the limits of integration, we get negative 1 over n squared pi times the quantity cosine of n squared pi x2 minus cosine of n squared pi x1. Distributing the negative sign allows us to rewrite the expression as 1 over n squared pi times the quantity cosine of n squared pi x1 minus cosine of n squared pi x2. We substitute this result back into the summation, ensuring we account for the initial factor of 1 over n squared. Combining the powers of n, we arrive at our result. I equals 1 over pi times the sum from n equals 1 to infinity of cosine of n squared pi x1 minus cosine of n squared pi x2, all divided by n to the power of 4. In conclusion, the integral of the function r of x over the segment x1 to x2 is given by this expression. Note, it is worth observing that the resulting series converges rapidly, proportional to 1 over n to the power of 4. This demonstrates how the integration operator acts as a smoothing filter. While the original series converged as 1 over n squared, the integrated series exhibits significantly faster convergence, making it highly efficient for numerical approximation. To conclude this lesson, let's visually reconstruct the Riemann function, r of x, to see exactly what we have been analyzing. We begin with the first term of the series, where n equals 1. At this stage, it is simply a smooth sine wave. Adding the second term, notice how the fundamental shape begins to distort. As we add the third and fourth terms, smaller and more rapid oscillations appear, layering detail onto the curve. Now, let's increase the number of terms significantly. With 30 terms, the true nature of the function emerges. Notice the jagged, fractal-like structure. While this function is continuous everywhere, visually it reveals the infinite complexity hidden within that simple summation formula. Thank you for watching.